last class we have to discuss the various examples of a group, show that the some of them is group, some of them is not a group. Now we have to now today in this lecture we have to discuss about the group of integers modulo and under addition and multiplications. So before this is the we just said that an example which is particularly important for applications in computer science and cryptography is a group of integers modulo and under addition. So we have to just say that is a this applications for using the coding theory, computer science, cryptography of groups of integers modulo n. So before going to the group of integer modulo n, we have to define some basic definition of this. The first definition is a congruent modulo of n. For n greater than equal to 2 be an integers, if x and y are the element of a z, then we say that x is congruent to y modulo n, and we write x is congruent to y modulo n in this way. So we say that if n divides x minus y, that is x and y have the same remainder when divided by n. So x congruent to y modulo n means we can say that this n should be divides x minus y, and or other way we can say that x and y have the same remainder when we divided by n. For example, 8 is we take x is 53 and y is equal to 21 as n is equal to 8. So add 8 divides 53 minus 2. So we can say that 53 minus 53 is congruent to 21 for modulo n. Other way in the second part we just say that putting another way 53 and 21 both have the remainder 5 when divided by 8. So 53 congruent to 5 mod 8, 21 congruent to 5 mod 8. When we divided 53 by 8 is we getting the remainder is a 5. 21 is divided by 8 also getting the remainder is a 5. So in this case we have to reduce the remainders and write into this form is this. So we can say that if the both the set is remainder is same remainder, then we can say that 53 is congruent to 21 mod n. This is the example of this thing. So clearly you have to just say that x and y is congruent. If we have to both the way we have to verify this. Now this is the theorem. So you have to study in this thing. We have to use this theorem. So let n be a greater than equal to 2 be an integer, then x congruent to y mod n is an equivalence relations on a z. The equivalence class of a consist of all integers having the same remainder as x when divided by n. Now we have to proving this result. We have a n greater than equal to 2 be an integer, and this statement is this x congruent to y mod n is equivalence relations. And so equivalence relation means we have to satisfy the three properties. If it is this relation is reflexive, symmetric and transitivity property. Let us try from the first is reflexivity is there because n always divides 0. So 0 can be written as x minus x. So n divides x minus x. So this means clearly we say that x congruent x mod x is a x congruent to x mod x is there. Symmetry case we have to just say that if x congruent to y mod n, so we say that x congruent to suppose x congruent to y mod n. If this means n should divide x minus y, and this can be x minus y can be written if n divides x minus y, so n also divides minus x minus y, minus times of x minus y because it's integers, and this can be written in the form of this should be written in the form of y minus x. So n should divide y minus x. If n divide y minus x, so we can say that y is congruent to x of mod n is there. So reflex symmetric condition is also satisfied. Now for a transitivity we have to say that x congruent to y, suppose x congruent to y mod n and y congruent to z mod n. So if x congruent to y mod n, we can say that n should divides x minus y, and also x should divides y minus z. So if n divides x minus y and n divides y minus z, then n should divides sum of these two. So n should divide x minus y plus y minus z, but x minus y plus y minus z is equal to x minus z. So n should divide x minus z. So if n should divide x minus z, in this case we can say that simply x is congruent to z. So the third conditions of this transitivity is also satisfied. So if x congruent to y mod n is an equivalential relation, and the statement of the equivalence class follows from the definition of this thing. We have to just say that, leave this into a as a exercise for you. You have to just try as a statement equivalence class is there. Now we have to another definition. We say that simply is an integer. The set of integers modulo n denoted by Zn is the set of all equivalence classes of a Z with respect to equivalence relation. So x congruent to y mod n, we call these congruence classes modulo n, especially we have to write into Zn is equal to collection of all equivalence classes is there. 0 is equivalence class, 1 equivalence class, 2 an equivalence class of n minus 1. And this Zn is the set of all equivalence classes of a Z with respect to this equivalence relation, this x congruent to y mod n into this form. So let us define, let's example Zn is equal to equivalence class of a x, x is equal to is the element of a Z. So we suppose n is equal to 4, so we claim the Z4 is the equivalence class of a 0, equivalence class of a 1, equivalence class of a 2, and equivalence class of a 3. Let us try this. We have to just say that equivalence, suppose I equivalence class of I can be written as a 0, because n is equal to, we have a 4, so 0 plus I and minus 4 plus I plus minus 4 this I plus minus 8 plus I, and then in general we can say that 4q plus I, where q is any integer for all I is the element of a Z. Suppose we have to just say that let this n lies between 0 to 4 and m n is less than m is less than 4. Suppose we have to take two equivalence classes, n and m are the same, then m is the element of a in equivalence class of a n, and so 4 should divides by m minus n. This contradicting this since this m minus n is less than or equal to 4, so 4 cannot divide the m minus 4. So hence the equivalence classes this 0, 1, 2 and 3 all are distinct. So clearly we have to just show that all the equivalence classes, these are the equivalence classes of a Z4 are, and this all the classes are, we have to show that easily, we have to show that is a distinct class, all are distinct. For example, I is equal to 0, so we can write 0, and this is 4, 8, and similarly we can show that minus 4, minus 8 and so on. If for I is equal to 1 equivalence of 5 is equal to 1 is a 5, 9 and so on. For equivalence class of a 2, 2, 6 and this all this thing. Equivalence class of a for I is equal to 3, we have a 3, 7, 11 and minus 1, minus 7. In this way we have to collect all the equivalence classes of a this. This all are the different. So we have a 0, 1, 2 and 3 are the equivalence classes of a Z4. So now another very interesting examples we have to discussing in Z10, in which of the following equivalence classes are equal: equivalence class of a 2, equivalence class of a minus 5, equivalence class of a 5, equivalence class of a minus 8, equivalence class of a 12, equivalence class of a 15 and minus 3, 7 and 22. So let us begin. We have to just say that we note that 2 equivalence class of a 2, because we have n is equal to 10. So equivalence class of a 12 is also the same. We have to write equivalence class of a 10, 2 plus 10, and that is equal to, we have to say that is a 12. So 2 equivalence class of a 2 and equivalence class of a 12 are the same. Similarly, minus 8 can be written as a minus 8 plus 10 is equal to 2, equivalence class of a 2 and minus 8 also the same. And then we have a 12, 12 plus 10 is equal to 22, equivalent class of a 22 and 12 is also same. So equivalence class of a 2 is the same as the equivalence class of a 12, equivalence class of a minus 8, and equivalence class of a 22, and these are the equivalence class. Now we have to think is a minus 5. So minus 5 plus 10 we have to is equal to 5. So minus 5 equivalence class is the same as a 5, and 5 can be written as a 5 plus 10 is equal to 15. So equivalence class of a 5, equivalence class of a minus 5, and equivalence class of a 15 are the same as this. Now we have to left only the 7 so and 3. So minus 3 can be written as a minus 3 plus 10 is equal to 7. So minus equivalence class of a minus 3 and equivalence class of a 7 are the same. So but equivalence class of a 2 is not equal to the equivalence class of a 5. Equivalence class of a 2 is not equal to equivalence class of a 7, and equivalence class of a 5 is also not equal to the equivalence class of a 7. So we have a this form is we can say that the equivalence class of a 2 is the same as this set, and these 3 are the same, and then 3 and minus 3 and 7 is also the same. So then in Z10 these are the same equivalence classes. There is different equivalence classes as 2, minus 5 and minus 3 are the, we can say that 2, 5 and 7 are the different distinct equivalence classes we have to distinct. So we just say that now we can move further. We can define addition and multiplication on Zn. These work obviously way. So we have to take equivalence class of A under addition modulo n, equivalence class B we have to define simply A and B when divides over modulo n. A multiplication this A dot A into B equivalence class, and we have to divide it by, and the remainder is this thing. Now for example Z9 we have a equivalence class of a 5 under addition modulo 4, 5 and 4. So we have to just say that Z9. So we can say that this is a set is a equivalence class of a 0, equivalence class of a 1, and so on. Equivalence class of a 8 is there. So this is the set for all Z9. So if we take an equivalence class of a 5 under addition modulo 5, the 5 plus 4 is equal to 9. So 5 plus 4 is 9 divided by 9, remainder is equal to 0. So this is equal to equivalence class of a 0 is there. If we have to take a multiplication, 5 under multiplication modulo 9, 4 is equal to 5 into 4, this is equal to 20, and divided by 9, remainder is equal to 2. So this product is also giving into the form of a this. So addition and multiplication is this. So now natural question is this. I have to just say that this result we say that for any integers n greater than equal to 2, addition and multiplication on Zn are well defined. So we have to define in this form. Suppose addition and multiplication is this. So we have to first we define that this addition is a well defined. So we take suppose for well defined nets we have to prove that in this form x1 congruent to x2 mod n and y1 congruent to y2 mod y. Then clearly we say that x1 plus y1 minus x2 plus y2 can be written in the form of x1 minus x2 plus y1 minus y2, and we can say this simply is this. If x1 congruent to x2 mod n, then n should divide x1 minus x2, and y1 congruent to y mod n, then n should divide y1 minus y2. So if n divides x1 minus x2 and n divides y1 minus y2, so you can clearly say that n should divides x1 plus x1 plus y1, and if this n divide this, n divide this is n also divides the so n should divide the sum of x1 minus x2 plus y1 minus y2. So if this means n should divide for the whole thing is this, n should divide this. So if n should divide this means n should also divide for this. So n should divide x1 plus y1 minus x2 plus y2. So in this case we can say that if n divides this means we can say that equivalence class of this is the same of equivalence class of this. So if we take a x1 congruent mod x2 is defined into this way. So this means addition is a we have to define is a very well defined is there. So if we have a next we have to just try to show that the multiplication of z involve also well defined. So we assuming this again x1 x2 congruent mod n, y1 congruent y n. So we take a product of a x1 y1 minus x2 y1. This can be written in the form of a x1 y1 minus x1 y2 plus x1 y2 minus x2 y2. So this can be written into this form, and because if associativity condition we have to remove this is the same into this form written, and we take x1, so y1 minus y2 and this x1 minus x2 into y1, and this term is divided by n, and this term also divided by n. So you know that n should divide, we know that n should divide x1 minus x2, and n also divides y1 minus y2. So we can simply say that this 2 is, so we can find that n1 n should divides for whole is this form, and then if it n should divide this whole, then we can say that n should divide into this is also. So n should divides x1 y1 minus x2 y2. So we can say that simply that the equivalence class of a x1 y1 is the same as a x2 y2, and multiplication is also well defined in this case. So we say that the binary this set of integer and addition modulo and multiplication modulo are operation we have to define, they are well defined operation is there. So now if they are the well defined operations, so my question is this, define a binary operation into this. We already show that this is a well defined operation. So option we have to question is this Zn under the binary operation is a modulo n is an abelian group or not. So we have to try. The first one case is closeness is very trivial by the definition of this. We have to show this is well defined. So a plus b is also the belongs to the Zn. So a congruent a plus mod n is satisfied. The closure property is clear from the definition of this addition modulo n is there. Now for associativity we have to try very simple. We take three elements a, b, c belong to the Zn. We try to a plus b plus c, and then we have to just say that applying this can be written as a plus b addition modulo n, and the definition of a plus modulo n, and then again we have to this, and then again by the modulus of this, and these a, b, c are the element of a z. So a, b, c are the integers. So under integers under addition is associative. So we can say that a plus, this can be written as use the associativity condition here, a plus b plus c. So if a plus b is there, then we have to apply the definition. We can add a plus, and that we have to write is a b plus c, and then we have to just say that a and this can be written in the form of a b plus c over n. So this means we have to by the definition of a addition modulo n, we can say that Zn under addition modulo n is clearly is a associative condition satisfied. So first we show that the commutativity conditions for all a, b belongs to the Zn, then a under addition modulo b can be written as b, and a and b are the set of integers, and set of integers under addition is a commutative condition. So this can be written as a b plus a. So we write a equivalence class of a b under addition modulo a is satisfied. The commutative condition, the Zn under addition is also is a commutative. So we have to now find the existence of identity. So we clearly 0 is the element of a Zn, for all a belongs to the Zn. If we write a addition modulo n 0, a plus 0, and this a plus 0 will be equivalence class of a, and this 0 plus a also is indicated in this form. So equivalence class of a 0 is the identity element. So we have to show that this 0 is the equivalence class of a 0 is the identity element of a Zn under addition modulo n. Now we have a last property we have to verify. This is the inverse is exists or not. If A is the element of a Zn, then minus equivalence class of minus A is also the element of a Zn. If we have to A addition modulo n minus A, this is A minus A because A is the set of integers, minus A is also set of integer, set of integer under addition is so we have to take a 0, and that 0 this A and this minus A is the inverse of A, that means is giving the identity element is 0. So similarly minus A plus A is giving the identity element 0. So this is equivalence class of A under addition modulo equivalence class of A by the definition of this thing. So this equivalence class of a minus A is the inverse of A. So we have to satisfy the close this Zn is closed under the addition modulo and Zn is associative under modulo and is commutative condition is also satisfied. Identity element is exists and the inverse is also, as every element has an inverse. So all the properties of a group is satisfied. So we can say that this Zn under addition form an abelian group. Okay, so let us what thing about this Zn under multiplication. So Zn under multiplication is not a group under multiplication of a modulo n. So why this is not a multiplication under multiplication is a modulo and form a group. So since one equivalence class of a 1 is the element of a Zn is the identity element, but 0 has a no inverse under multiplication. So we cannot find any element if we have a we take a 0 equivalence class of 0 into any equivalence class we have a this is giving you a 1. So in this case we have to also this base multiplication n. So this can be written in the form of a this is 0 into a and this is equal to 0 is clearly not giving you a equivalence class of a 1. So for any element the 0 does not has a inverse under multiplication of a modulo n. So that means naturally questions come in the mind when this under multiplication modulo is a group or not. So when does the element of Zn has a multiplicative inverse is there. So for this we have to write a one theorem is saying that I am not going to prove this theorem, but I just use this theorem कि A and B are the element set of integers and not both not equal to 0, then A and B are relatively prime if and only if there exists an integer x and y such that ax plus by is equal to 1. You can easily prove this result, but I am not going to prove in this course, but we have to say that A and B, if two A and B are relatively prime, then we have to say that there exists some integers x and y, ax plus by is equal to 1 is there. So we have the following lemma giving the answer of our questions when we say that when the multiplicative inverse under multiplication modulo is exists or not. So let A be the element of a Zn and a equivalence class should be not equal to 0. So we have to restriction our case is A is not equal to 0 and we have to say that A belongs to the Zn has an inverse if and only if A and n are relatively prime. So we say that if Zn is there, A is non-zero, A not equal to 0 is the element of A, and then A belongs to Z has an inverse is exists only if A and n are relatively prime. I have to prove this this theorem, this lemma very so first A is the element of a Zn and equivalence class should be as not equal to 0. So suppose we assuming that A and are relatively prime, so then there exists a integer b and s belongs to the z, then the theorem we have to just state, I say that ab plus ns is equal to 1. We can say that if a and are relatively prime, there exists an integer x and y such that ax plus by is equal to 1. So using this theorem we can say that if a and are relatively prime, there exists some integer b and s belongs to the set of integer. So a b plus ns is equal to 1 by that theorem, and from this we can say that clearly we say that ab minus 1 is equal to ns, if ab minus is equal to ns, this implies that a dot b is congruent is equal to 1, and if a b is equal to 1, we can say that a dot b is equal to 1. So n should divides ab minus 1. So this n is s, this n should divide this. If n divides from ab minus 1, so a dot b is equal to 1. So and that we can say that a that is equal to 1 is clearly in this form. So we have to just say that since we have ab is the a and b are the element of a set of integers, so under set of integers elements are commutative, so a b is the same as a ba. So we also have a b dot under multiplication ba, and then is satisfied, this condition is there. So we have to just say that under these conditions, so does there exist element b belong to such that a equivalence class of a into equivalence class of a b is giving 1, the same as a b equivalence class b into a is equal to 1, then element a has an inverse. So we have to find a certain element equivalence class b. We show that if we multiplied this with the equivalence class of a under modulo n, and that is giving the equivalence class of a one identity element of a that set under Zn under multiplication. So inverse a has an inverse is there. Now conversely, suppose that we have to other way we have to assuming that conversely suppose a has an inverse, then we have to say that a and n are relatively prime. That is trivial. Suppose a is an inverse, there exists a b, some element b belongs to the Zn, such that a and b is equal to giving you an identity element 1. If a and b giving the identity element is equal to 1, then we have to show that a n should be divides a minus b. This can be written in the form of a, we say that a and b, so this can be written in the form of a dot b equivalence class of a dot b under multiplication over this. So we just say that simply is we say that in the form of n should divides n should divide the a minus b ab minus 1. If n divides ab minus 1, then ab minus 1 can be written as some ns for some s is the element of a z. If ab minus 1 is equal to ns, then we can say that ab plus ns is equal to 1. If ab ns is equal to 1, so we can say that by the theorem again a and b are a and n are relatively prime is there. So in this case we have to this theorem is very trivially we have to prove that by using that lemma as proved by the using this theorem. Clearly we said that if we have to inverse of its exist if a and n are relatively prime. So we say that under multiplication inverse of a Zn inverse is exists only in the case we say we have a element of a and the n are relatively prime is there. We see in general not every element in Z star n we have to take a Zn minus the equivalence class of a 0 has an inverse. So in general not every element Z star, if we have to eliminate the 0 in this Zn has an inverse. For example, if n is equal to 6, the only element of Z star 6 that have an inverse are 1 and 5. 1 and 5 are the inverse, but no other element. 2 does not have an inverse, 3 does not have the inverse. So we have to just say that hence in general Z star n under multiplication n is not a group. It is group only because you can see why every element of A has a not a inverse, because we take Z6 n is equal to 6 and 2 and 6 are not a relatively prime, so inverse of a 2 does not exist. So we have to just say that 1 and 6 are relatively prime, 5 and 6 are the relatively prime, 4 and 6 are not a relatively prime. So in this case we can say that not in general Z n star under multiplication modulo n is not a group in general. We have to just say that. So now this is we have to say that when this thinking about the group, so we have to define a new set, Un be the set of all elements of a Zn star that have an inverse in this. So UNS, we have to take a set where X equivalence class of X is the element of a Zn star, and X and N are relatively prime. So for example, we have to just say that U4, then the elements of U4, the elements of a U4 we can write the elements equivalence classes which are relatively prime to 4. 1 and 4 are relatively prime. 2 and 4 is not a relatively prime. 2 is not the member of this set. 3 and 4 are the relatively prime. So 3 and 4 are the, so we have to 3 is this thing. So 1 and 3 are the elements of this set, and similarly U9. So U9, all the factors which is 1 to 9 which are relatively prime to 1 to 8, all the factors are which are relatively prime to 9 is the member of this U9. 1 and 9 is relatively prime, 2 and 9 are relatively prime, 3, 9 not a relatively prime, but 4 and 9 are relatively prime, 5, 9 relatively prime, 6 no, 7 and 8 are the relative prime. So U9 are the member of a equivalence class of a 1, equivalence class of a 2, equivalence class of a 4, 5, 7 and 8. These are the equivalence classes of a this U9 in this case. So we can see now inherent multiplications but not addition, and a multiplicative identity from Zn, and every element in Un has a multiplicative inverse by the lemma. We have to prove this because Un is the element such that we have a collecting the set in this form where n and clearly this set X equivalence class of X and N are the collection of only those elements. We have to equivalence class X with relatively prime to N is the member of this. That means the lemma is saying that under this, if we have a X and N are relatively prime, then every X has a inverse into a in this case by the lemma. We have to prove this thing. So we see that for this 2 and 3, 2 is inverse of a 2 is 3 in U5, and inverse of a 7 is 3 in U10. U5 means we have to just say that U5 we have to take as a 1, and we have to write a 2, we write as a 3, and we have a 4. Then all are the relatively prime to this. If you take, we have to take a 2 into 3 under multiplication modulo 6, this is 6 is equal to, you have a 5. So multiplied identity, you have a 1 here. So we can say that, sorry, this one we can just say that this. So 2 into 3 is equal to 1. And similarly we can say that 3 into 4, that is giving you a 2. So this is 3 is not a inverse of this, but you can say that 4 into 2, 4 2 is 8 is equal to 3. So 4 is also not. So inverse of a 2 is a 3 in 5, and 3 is the inverse of a 2. And if we take a U10, if U10, U10 is the element of this, which are relatively equivalence classes of relatively prime to 10. We have a 3, and we have a 4, no 5, no 6, we have a 7, and then we have a 9, and these are the elements of this. So 7, inverse of a 7, if we take a 7 into 3, that is equal to, you have a getting again is a 1. So we can say 7 is a inverse of a 7 is 3, and inverse of a 3 is also, we can say that is a is equal to 7 is there. So we see that the elements has a relatively prime, and elements has a inverse is there. In here we have to just in this case we have to just say that 2 and 3 are the inverse. Inverse of a 4, we have to just say that 4 into 4, 16 is equal to 1. So inverse of a 4 is itself. Inverse of a 5, 3 and 2 are the inverse of each other, and 4 is itself inverse, 1 is itself inverse, because we have to take a in for U5, 4 into 4 is equal to 1, so 4 is itself inverse. In this case we have a 9 into 9 is equal to equivalent to 1, again equivalence class of a 1. So 9 is a self inverse, 3 and 7 are the inverse. So we have to just check and all of them into this simply this thing. So these are the inverse of this set, we can say that. So I think I have to stop here today this lecture, and in next lecture I have to, by this we have to set of the finite set. We define the next class is a finite sets, and some explain about the Cayley theorem and finite groups. We have to discussing about the some examples of a finite group. Now we have to using today's examples, these two lectures by examples of a group is all are the infinite examples of a group, and in the next lecture we have to define the when we say that the group is a finite, and also we have to discuss the some examples of a finite groups, and also we have to discuss the properties of a group. Thank you very much.